The last type of problem that we'll have for statically indeterminate axial bars, I typically call the rigid link. And they typically look something like this. There's either a horizontal bar that's rigid, like so, that probably has a pin connection somewhere, like this, and that's not the axial bar. That is the rigid. And it's linking the elastic system together. So we might have one axial bar that's supporting it this way, and then maybe another axial bar that's supporting it this way, and there's a load like so. So the link connects the axially loaded bars. So the link is not deforming, it's these two that are stretching and deforming and resisting. So these guys are the axial. So they stretch, deform, result in the load that's going to deform, that gives us then the resistance to the applied load. Once again, what I'd like to do is to kind of use a teaching example, and I'm going to use one that's a little bit harder than the one that I just sketched out, and that's going to be a length that looks like a big L. Like so. And then we're going to put a pin right there. So it is a rigid link, so that's the rigid part. And then what we're going to do is we are going to put a load, or pardon me, a bar here. So there is one axial bar. And let's go ahead and say that this length of this bar is 5 inches. And then I'm going to put another link right here, a little bit longer. Let's say that that's going to be 6 inches. Let's call this B. Then at C, which is exactly halfway down, I'm going to put a 4 kip load. And these distances then we're going to call 4 inches. And then the distance that we've got from here is going to be 12 inches, like so. All right, so we'll go ahead and kind of label these things. We'll say that, let's call this bar number 1, and then we'll call this bar number 2. So as you can kind of tell, this bar wants to rotate, but it's being restrained by these particular forces, by these particular axial bars. So I think we've got all the pertinent labels on there. B, C, let's call this D, and then point F. Let's try to get rid of calling that an E value. All right, so bar number 1, that has the following properties. The area is 1 square inch, and the E is 20,000 KSI. Bar 2 has an area of 2 square inches and an E value of 30,000 KSI. And there's no gravity in this case. You could either say we're turning gravity off, or this thing is deforming in the horizontal plane. So we're actually laying this down on the table and doing something like that. So we'll say no gravity. Almost always in this class, if we don't specifically state it, we're neglecting gravitational effects. And what we would like to find, then we want to find the stress in both bars. So sigma in bar 1, I'll put the parentheses, sigma in bar 2, and the horizontal displacement of B. It's going to the right, like so. All right, now here is the key to this sort of problem. You need to draw the displaced state. And the reason that that's important is it's going to help you with statics and it's going to help you with compatibility. So when we do that, and I'm going to go ahead and draw this on another figure. It was here, and there's a pivot right there. So when it deforms, it has to move still at a right angle. So it's going to move this way and then this way, like so. So it stays at its right angle. So it rotates as an L. So it stays rigid. That's crucial when we do that. So this displacement is what we're calling delta B. And then this displacement, we would call that delta at F. That's how much this bar is shrinking. This amount is how much this bar is stretching. So the two bars are actually bar 1 is being compressed, bar 2 is being stretched. So again, this is 2, this is 1. All right, that's one thing that it shows us. But the other thing that it does is it tells us the direction of the forces. So I'm going to draw this one more time now with the forces on it. It's like so and like so. Well, as bar 2 is stretched, it's in tension. It's pulling it back this way. So that's going to be the bar force in, pardon me, that's the second bar. And then this one, P1, is being compressed. It goes up. So the induced forces act against the motion. And then our 4 is here. Then we have our Rx and our Ry. So that would be our free body diagram then that we would have. So again, that one is going to the right. So the key is that the bars resist the motion. Notice the bar is rotating. We're assuming it's rotating it clockwise. The P1 wants to go the other way. So does the P2. So they're going in the opposite direction. Now in this sort of problem, it's almost always true that you want to apply a moment equilibrium rather than a force. If we did force equilibrium, we would bring in Rx and Ry. We don't want to do that. So what we're going to do is we're going to sum moments about the pin, which is point D. So I'm going to sum moments about D, and that's going to be our one equation of equilibrium. And that is very common for the rigid link. So for the rigid link, it might be counterintuitive because we have axially loaded bars, but it's actually a moment equilibrium statement that gives us that. So if we take this sort of that direction of moments is positive, I have 4 times 4 from the applied load. So 4 times 4. And then the opposite, I'm going to have minus P1 times 12 minus P2 times 8. And all that's equal to 0. So that would be our statement of equilibrium. And it is a moment equation, but notice what it does. It weaves in, or it somehow connects the axial forces in our two axial bars. So that is statics. This is our expression of A, statics. All right, so that is linked with our free body diagram. We have statics, we have one equation, 2 unknowns. So that's why this problem is statically indeterminate. The second thing, so that's our A, our B is going to be stress strain, and we're kind of becoming old hands at this. So what we're saying is, and this is kind of crucial, we're going to assume now that we've already worked out the signs of P1 and P2. So we're going to treat both delta B and delta F as positive numbers because we're just looking at those and I know that they're going in the direction shown. So I will just write then that delta B is going to be equal to P2, that is the force in bar 2, times its length, that turned out to be 5 inches, divided by its area, that's 2, and its modulus elasticity, 30,000. So that would be my first statement of my stress strain law for that particular bar. So that's the delta B, and again, that's the stretch in bar number 2. They're the same thing. They mean the same thing. Then delta at F, that's going to be a same idea then. That's going to be F1, or P1, pardon me, times its length, so that's going to be 6 inches, divided by its area, 1, times its modulus elasticity, 20,000. So those now are the relationships between the displacement and the force. All right, so now we need a statement of compatibility, C. And here is the key. So remember, compatibility for the fixed was that the total bar stretch was 0. For the composite bar, it's that the displacement in material 1 is the same as material 2. For the rigid link, the key phrase is going to be similar triangles. And I'm going to go back to this shape right here just for a second. Notice that these triangles go at some angle, and that angle is theta. We don't really need theta, but it has to rotate the same amount. So I would say this distance, again, the tangent, this distance is to this, as this distance is to this. So we use the tangent of the angle to craft out the similar triangles. So I would write that, and it's always going to be like that. You're always going to have a similar triangle on these rigid links. So again, you need the displaced shape. That's why it's so important. So that's going to be the following. We'll have delta 1 is to 12 inches, as delta 2 is to the 4 plus 4, or 8. And that's going to give us then the delta 1 is 1.5 delta 2. And then our expressions go in here for the delta. So the delta 1, this is really, I guess we're calling it delta 1 is really delta F, I guess, the way we've been calling it, is 1.5 times delta at B. So we use those, and we substitute in, and it all becomes algebra. So after that, we go ahead and solve this. They go into equilibrium, and then we solve for the forces, and then once again, it's off to the races. Okay, so since we're wrapping up 12 and a half, I still owe you a little bit, but now you'll have a chance to go through these and practice them on the homework, give them a shot, and I'm actually going to assign 2 for these so you get a little bit more practice, and we'll review this again next time. But for right now, that's it.